Now we will start with convolutional neural network. So we have already seen what is a convolutional neural network. We will try to understand this with a very shorter architecture over here, how the implementation works, and then we will start implementing the convolutional neural network. We are going to see the two most popular convolutional neural networks, that is LeNet and one which is VGG16 model. We will try to understand all these models, and with this you will be able to implement any kind of convolutional neural network over an image data. So what is convolutional neural network? So convolutional neural network involves two parts. First is the convolutional part, and the second one is the neural network, which is our normal traditional ANN network. So in the convolutional operation, in the convolution part, we will apply a convolution operation, and in the normal part, in the ANN part, we will just apply an artificial neural network, a normal artificial neural network, whatever we have developed or learned earlier in the previous classes. Convolutional operation usually happens over the image data. It is very well worked out on the image data. All the image processing algorithms, all the image identification, classification, operations, everything that you can see on the internet right now with respect to images, where it is automatically classifying something as some category or some other category, is using convolutional neural network in the backend. So this is the backbone of image processing in the today's world, and that's what we are going to learn today. So first thing that we are going to understand is it works well on the images. So let's start with an example, which is an image. So here we have an image which is of a zebra, and on this image we consider this image as our input data. So our input here is an image, and on this input image we are going to apply the convolutional operation. So the convolutional operation start with identifying the convolution operation starts with identifying patterns in this image. Okay, how does this happen? So it happens with the help of kernel technique. In the kernel we have in the kernel technique we do extractions of important features from these images and preserve it into a array. So first thing is that image that we can see in front of us is a formation of three parts. It is the rows, the columns, and third is the channels. So image is formation of three parts: width, height, and channels. So what are these channels? Channels are every image is constructed with the help of three channels, that is red, green, and blue, and that's how any image is getting distributed. So we have three channels, and for these three channels we are going to apply a kernel over the three channels. So the first channel will be of red, second channel will be of green, and third channel will be of blue. So these channels are important to identify, distinguish anything between with respect to colors. Now a image can be split up into three parts, that is red, green, and blue. Now in a kernel, so kernel is a formation of a matrix. It is a matrix which which has certain numbers. These number represents a particular feature. So it can be, this number can be like cross. So if I am trying to identify a cross, just give me, so say I want to extract something from this data. I want to extract so this is my image, and I want to map this image with respect to such a line. So 111 represents, there is this horizontal line. Okay, so this particular matrix that we can see is a kernel. Kernel sees that what is happening, what we are trying to identify. So we are identifying a line. Okay, so this kernel is nothing but line, where this 111 represents this line and 000 represents that there is nothing in this part. So I am identifying kernel, this line in my image. So I apply this convolution operation on this each and every part of this image. I will constantly keep on applying it over the entire parts. Now what happens in this? So say my image has just a minute. So here we have an image, and in this image line is present in this part and this part, and I am detecting line in each and every space. So in this space line is not there. So when we apply the convolution operation, so this line basically represents 1, 1 and 1. So 1 is not present in this place. So I will multiply this entire values with this values in this corner. Okay. So I am applying convolutional operation. So here the empty space basically indicates 0, 0, empty space is 0, and this line represents 1. So line is 1 and rest other part is 0, 0, 0 and 0 below as well, which means when I do cross multiplication of this array with this part of the image, so the resultant will be 0, which means I have not detected anything, I have not detected a line. So then I move forward in this region and I will do the cross multiplication of these values with the values in this array, and again I have not detected anything. Similarly it keeps on happening. Okay, the size of this image, say it is 10 by 10, when I apply the convolution operation it may become 5 by 5 or 3 by 3 or 7 by 7. Convolution operation is to minimize the unnecessary information in a data set. So we apply this convolution operation over this data set in each and every corner of this data set, in each and every corner. And once we apply this in each and every corner, so when we reach at this corner it will tell us that yeah, some line is represented here. So here it will just give out a value as 1. Here it will return 1 and rest other values will be 0, 0, 0. So shorter version of the image tells us that we do not have anything in the corners, we have the line, or this line was present at the center. That's why we are getting a new matrix which is shorter version of this. This was 10 by 10 array and the new array that we have, say it is 5 by 5 based on the kerneling operation that we are applying. Now while we are applying this kernel operation, there are two things that we have to keep in mind. We have already discussed this in the theoretical explanation. First thing is how much gap we are taking at every corner. Okay, so at every, so first box is this, so second box is just after this first row, or it is directly after 2 rows. Okay, so this particular thing that we are going to talk is stride. So stride is how much stride is all about skipping out search in that particular. Striding is skipping out searching certain rows in that or columns in that particular array. So stride usually the search process goes like this. It will search in all these corners first, one by one, and then it will go down. So it is vertically going in this horizontally going in this direction, and vertically it is going in this direction, which means the movement of this kernel or the multiplication operation of this kernel is going to happen in each and every corner. So stride will tell me that should I do it in each and every corner, or is it fine to skip certain columns. For example, if I am doing search in this column, so if I am putting stride of 2, so it will say stride of 2 or stride of 3. So if I am searching in this corner, if it is done, do I want to search from here, or do I want to skip some and I want to search here? So this operation striding will decide. So how much I have to move in this direction horizontally and how much I have to do in this direction. So the stride will decide the speed of kernel operation, and second one is pooling, padding. Second one is padding. So padding is all about helping the kernel to learn everything in the data. So when we are applying a kernel technique, for example, and if I am keeping stride of 1 unit in the horizontal direction or in the vertical direction, so what will happen is it will skip one row at a time. Okay, it will skip one row at a time, it will skip one row at a time, and it will keep moving forward in the right direction as well as the vertical direction below. So while this is happening, it will be able to search more in this part or the central part, but it will skip out the corners. But if you want to the algorithm not to skip the corners as well, so we can add a padding. Padding is all about adding an extra layer, on top of our array. So this is our array, so any image can be transformed into an array. So this array, in this array I am adding a padding layer. Okay, so we are adding a padding layer on top of this array. While we are adding a padding layer, so it will now not, it will skip this part. Padding is all about having zeros, increasing the dimension of this image and having zeros on top and below and all the corners. The values will be zeros in all the corners. So when I apply convolution operation, so it will search more in this region, search here, and likewise it will keep on search here, or search the kernel feature into this, and it will search here again. So while this is happening, it is not skipping the central part, which means it is now be focusing more on the central part as well as corners of this image, which means when we are applying padding, it will do extensive search in the central part. This becomes the central part and the padded region becomes the corner. So it will now skip the unnecessary padded value and it will search more in this part where the image is actually there. So padding is done to avoid the kernel or feature mapping skipping the corners. So when we are doing normally over in data, it will skip the corners, but when we add padding, it will skip the padded part, or it will search less in the padded part. So that is the benefit of adding padding. After that, once we do have this convolutional operation or the kernel feature mapping, so whatever is the output array, we will do pooling of it. What is pooling? Pooling is all about reducing the image dimension. So earlier this was 10 by 10 and I got an image as 5 by 5 as an output here. This is 5 by 5 say. So when I do polling, I will extract useful information from this 5 by 5 array and convert it to say 3 by 3. So pooling basically helps us to extract more information from this data, or it helps us to extract meaningful information from the data. So there are different types of pooling, that is max pooling, average pooling, min pooling. Usually we are using max pooling and min pooling, average pooling. So pooling operation will reduce the image further in shorter one, and we can have multiple convolution layers. So this is my first convolutional layer. So here we have this first convolution operation happening, convolution plus ReLU operation. This is the second convolution plus ReLU. This is the third. Why we are using ReLU? ReLU helps us to break the linearity. So we want to break the linear dependence or linear association among the data. That is why we need to put ReLU activation function as well. And once this is done, we get, say for example, I just remove this two layers. I am having a single kernel, single image. I am applying convolutional operation where I will apply the kernel method. I will multiply or search for features inside this data, and I will do the pooling, and after pooling I am getting an array like this. So what is this array? So I am getting an array of images, multiple arrays I will be getting. As you can see, multiple small arrays will be getting. So we have to feed this to a neural network architecture. So if I want to feed this image to a neural network architecture, I cannot directly pass this array to the neural network. So what I have to do is I have to flatten the image, which means whatever is the image, whatever is the array that we have got, we will flatten it, which means the array will be converted. So if say my array is like this, it has value 1, 2, 3, 4, 5, 6. So when I do flattening, it will become like this: 1, 2, 3, 4, 5, 6. my array will be flattened and it will convert my two-dimensional array into a single dimensional array. So that is what we are going to do in the flattening layer. Flattening allows to convert the data into one dimension. Why we are doing it? Because the neural network cannot accept two-dimensional images. Neural network needs one-dimensional information to do the processing. So now each and every attribute will be set out here as an individual input data, and the two-dimensional data will array will be getting converted to one dimension, and each and every value will become an input, and then we will apply a fully connected neural network. Now fully connected neural network, this is the same that we have seen the normal ANN architecture, and then we can use classification over it, and based on the probability value we will decide whether it is horse, zebra or dog. So this is the entire convolutional operation in short we are doing. So to sum it up, what we are doing is, a image is there, on it I am applying a convolutional operation. What is convolution? Convolution comprises of feature mapping certain features from the images with the help of kernel. Kernel will search the image features in that image, and if the features are mapping, it will get stored as numbers with the cross multiplication or the multiplication between the kernel value and that particular area. While it is doing, it may lose out the corners. To avoid it lose the kernel, what we can do is, we can use the padding process. Also, if I want to skip certain regions and move forward faster, which means if I want to do the search but I want to do a faster search, I can stride or increase the stride, which means I will now be not searching each and every corner thoroughly. I am just searching fastly and skipping certain rows from the data. So this entire operation keeps on happening, and once this is done, I will get an array. I will apply the ReLU activation function and I will get an array of features or reduced version of the images. So this image is there, reduced version of the image I will get. On this reduced version of image, I will apply the pooling method. Pooling is all about extracting meaningful or insightful information. So I can use minimum pooling, maximum pooling or average pooling. Once the average pooling, minimum pooling, maximum pooling, any kind of pooling which we are applying is done, I will convert the data. I will get an array, multiple arrays I will be getting for each and every aspects of this data, and this array, these all set of arrays cannot be directly fed into the neural network. So I have to convert it into flattened layer, which means I have to convert everything into a single dimension, and that's where I use flattening layer. Flattening will convert all the arrays into single dimension, and then we apply the fully connected neural network over that data, and we will get the decision whether it is horse, zebra or dog. So that is the entire CNN architecture that we have talked about. Now we'll start the implementation. To start the implementation, we will first import sequential from keras.models. Then we will import layers, which is convolutional 2D, max pooling 2D. We are going to import layers, that is activation layer. We are using flattening, we are using dense, we are using dropout. All these layers we are going to import. Then we are using import backend SK. Why we are using backend SK? It helps us to process the information or the image information while we are working on it. Then we will use image data generator. Now what is this image data generator? Image data generator is a part of data augmentation or image data augmentation. Image data augmentation is say for example I have an image, and I have an image of dog, okay, with me, and say if I have another version of the same dog, okay, zoomed version of that image, which means the face of the dog is big now. So this is also a dog and this is also a dog. The only difference is this image is a bigger one, but the dog size is small, and in this image the dog size is big. Sometimes what happens, like I have half face of the dog, and here I have full face of the dog, okay. So even if it is a half face, it is a partial representation of a full face. So this is also a dog and this is also a dog. So what happens, we cannot have all this possible set of data for the same image. if I have the same image and if I'm passing the same image in a different format, for example, the location or the position of the dog has changed and it has moved somewhere else, and if I'm trying to use that data to recognize or to make the machine understand or to identify whether it is a dog or a cat, my machine will not recognize it correctly because the position has changed. So image data generator helps us to generate multiple images. It is the augmentation process. It will generate multiple images of the image of all the dog set images. So a single image can be converted into multiple set of images with the help of images data generator. Some images will be zoomed up, some will be light colored, some will be blurred out, some will be partially shared. Shared means I will not have the entire image, I may have the some part of the image. Some images will be twisted because it is not possible that all the time the dog the images we are going to get is in the single structure only. It may be twisted 90 degree, 30 degrees. So a single image is converted into multiple images with the help of twisting, turning, sharing it out, or um, or just blurring it out or zooming the image. Then we are importing optimizer, which is Adam. Then we are using image to array. Image to array is used to process the image in image. So Keras dot preprocessing helps dot image has the image processor, that is image. It will convert the image into an array. We have Keras dot utils. We have to convert the data into categorical format. Now here we need to convert the data into categorical. So we will use two categorical functions from Keras dot utils. Then we have train test split. Now the images that we are going to get are not going to be in a form of Excel, right? The images will be stored in a form of directory. It will be stored in a directory. So I will call in the data images using this imutils path. So I will require the system path of that images, and I will use paths to get the images one by one into my Jupyter notebook for doing the pre-processing part. Then we have matplotlib.pyplot. In the pyplot, we use it for creating visuals or see the images. Then we have NumPy. We have argparse to parse the arguments. Then we have random, if in case we want to do the random shuffling of the images. We have CV2 to process the data. It is an open CV library which is very much effective in image handling. Then we have OS, if in case we want to get path of the images and work on the OS. So system related activity, operating system, OS will help us. We will import warnings, and we are using TQDM. So TQDM is a library which will help us to create a progress bar over the loops or the whatever operation we are doing. So we need a progress bar to just see, okay, how much it is done, how much it is pending. So for that TQDM will help us. We have iter tools which will help us to iterate over the data. Then we have TensorFlow as TF, which is our the base library for processing such kind of deep learning data. And we see the TensorFlow version, which is 2.1.2.0, which I am using. We filter the warnings and we ignore the warnings. It is essential because sometimes when we are running, you will get unnecessary warnings. So to change the warnings or remove it, we can use filter warnings. Seed we are setting it as 42 because we are using randomization here. So seed 42 will help us to use a random set of 42 number only. Here we are developing a model, that is a LeNet model, classification model. I will talk about this LeNet model further. Okay, we'll discuss LeNet model for now, and then we will talk about the image handling process and everything. So LeNet model is we are creating a class called as LeNet, and we create a static method, and this static method name is build, and in this build method we have width, height, depth and classes. Now width, height and depth basically helps us to tell the dimension of the image array, and here we take classes as an input, like what are the total classes. So if you are doing 3 class classification, so class will be 3, like dog, cat and camel. And if in case you are using something else, there are 4 categories, classes will become 4. So we are using sequential model or sequential architecture on which I will post one by one all the layers, and input shape is going to be height, width and depth for this convolutional operation. If k dot image data format, which means if the format of that image is not going to be channel is equal to channel first format, which means whenever we are storing the image, always we represent the data with the help of height of the image, width of the image and depth. But sometimes some image formats, the depth is at the first, we call it as channel first images. So for such images which is channel first format, so depth will come first and then height and width will be coming. So if it is a normal image, if we will put it as height, width and depth. If it is a channel first format image, the input shape will change. That is the only difference. Okay, so it will become depth, height and width. Okay, and once this is done, we will first create a input layer which is convolutional 2D layer. So in the convolutional 2D input layer, we are specifying the neurons as 20. We are specifying the kernel size as 5 by 5. We are using a 5 by 5 kernel to reduce or apply the feature mapping process. We are using padding the same, which means we are not going to do any padding over here. And input shape is going to be the input shape, whatever input shape is there. So whether it is channel first, channel last, whatever type of image is there, automatically it will change the channel and it will create an input shape. Then we are going to add activation function, which is a ReLU. We will apply the activation function ReLU because after the convolution operation, ReLU function will get activated, and then max pooling 2D we are going to apply. We are using the pooling operation to reduce 5 by, now once I apply a 5 by 5 kernel on an image, say the image size is 100 by 100, it will get reduced to 5 by 5. Say 100 by 100, it may get reduced to 50 by 50. Further, to reduce that image and extract only the meaningful information, we do pooling 2D operation, and pooling size we are putting it as 2 by 2. We are using a pooling kernel of 2 by 2 and it will apply with the help of strides 2 by 2. Strides 2 by 2, which means it will skip one row or one column. Okay, so when it is applying one column, it is going to strip in the horizontal direction and one column it is going to strip in the vertical direction. So both the parts, both the ways it is going to apply. Now the same convolutional neural network, here we have the input convolutional neural network. This is our next convolutional operation we are applying. Then we have the same convolutional operation. So this is a LeNet model which is developed by Yanlikod, and in this model these are certain variables, number of neurons, number of convolutional layers, these are fixed. So we cannot, we are just applying multiple convolutional layer. We apply 3 convolutional layer, and we, after the convolution operation is done, we flatten the image, flatten the array, all this operation. The more we add convolution operation, more detail we are going to check into that image. We apply this flattening, and once flattening is done, we apply the dense activation function. Dense activation function, basically we are taking, now we are starting with ANN. This is our ANN part. We apply ANN and we are taking dense of 500 neurons we are taking. Then we apply activation function ReLU. We can add multiple dense. The more dense we have, the more it will take time to process the information. Then the output is going to be softmax. So the activation function softmax we are going to use, and in the output we are using classes. So it is the same number of classes that we have passed as an input, and then activation function softmax will create 4 or 5 category or 3 category based on the number of classes that we have specified. At the end, this class is going to return a model. So this is how a model is getting constructed, a LeNet model is getting constructed. So we have created this LeNet model, which is a combination of multiple convolutional layers, activation function and max pooling. Similarly, we have this VGG16 model now. VGG16 is a graphical model, or visual geometry group, is a kind of organization or people who have created this model, which has 16 layers of neural networks, or layers, hidden layers. So it starts with a sequential layer, then we have convolutional layers with 64 neurons, 3 by 3 kernel. There are 2 convolutional layers parallelly, and then we have max pooling, again 2 convolutional neural layers parallelly, and then max pooling, and there will be some more blocks over here which will be more number of neurons. and more number of convolutional neural network, but ideally I have reduced it because ultimately it will take more time to train the data and the images over it, and it will just like the laptop will get hanged. So it is not possible to train on a multiple convolutional neural network. So actually it should have 16 convolutional operations, and then after doing all the pooling and all, there are 16 convolutional layers to be honest. Here we are having only 4, and after that we have this flattening and then dense. We are using 4096 because there is a huge amount of neurons will be required, huge amount of data is getting used, because image, when we convert this image into an array, even though it is compressed one, we will be having multiple arrays, and for multiple arrays there will be multiple input. So for that we will require more number of neurons. So that is why we have this 4096 neurons with activation function as ReLU, and we will use dropout directly. Again we have 4096, which means these two 4096 hidden layers having a dropout of 0.5%. Again we are using a dropout, and after this dropout we are using this output layer with number of classes as the same number of classes that we had here, and activation function we are using softmax because output is classification, so softmax is the best thing to use, and we'll use model, will return model as an output. So these are two classes, and this will help us create a model, data model, that is VGG16 or LeNet. These are two convolutional neural networks. Now we will use the dataset. We will read the dataset, and this is to store the model. This is to plot PNG. For now we will skip it. We are using epochs as 25, and learning rate we are using 10⁻³ which means 0.001, and batch size we are using 32. Now here we will start with working on the images first. So it is not the CSV file actually which we read with the help of pd.read_csv. It is a complex process because images are stored in memory location, and memory location we read the address of that memory location. So first we will store data which is image, and then we will store the labels of the data. So to store the data we will create an empty list, and in this list we will have multiple arrays, and these arrays, each array will represent an image. So every image will be broken down into 3 parts, that is 3 arrays will be that red, green and blue. So we will have array, first image array which will be 3 arrays of red, green, blue, second image array red, green, blue, third image, like that we will be having, and we are going to convert the data into form of matrix. So the brighter regions will be given as 1 or 255 as the value, and the lighter region on that image will be given as 0. So that's what we are going to do. And labels, it is a complex process. So now we will try to understand how we are going to do that. So first of all we will grab out all the image paths from our data set. So images are stored in a folder called as data set. So what is data set? Let's see. Data set, this is data set. Okay, what I am doing is I am trying to search the data set folder in my drive, okay, in my current working directory. So in my current working directory, which is, say right now I am on desktop, dataset and CNN project file. So if I go on desktop, let me go on the desktop part, and I'll go on dataset, and then I have CNN project. So here I have my file, and in this I am searching for dataset folder. So here you can see dataset folder is there, and in this dataset folder I have 3 folders, subfolders, which is forest, buildings and sea. And in forest I will have images of forest, in buildings I will have images of buildings, and in sea I have images of sea. So I want to extract all the image paths, all the images and its path. So I will first sort the images and I will sort it out. So I will create a list of all the paths which are present in this image path. So I will use paths.list images on this dataset folder. So I will be searching inside this dataset folder images and their paths. So say this is my image, okay, so its path, memory address, that I am going to store the address of that image I will be storing, into a list. Similarly, I'll do it for all the images and I'll store the paths of each and every images. I'm putting a random seed of 42, okay, to shuffle that image. Initially, I will sort the images when I'm collecting it, and then I will shuffle the images. After shuffling the image paths, we will now start with using or creating labels of that images. I just have the directory or the folder. I do not have labels like we have in the X when we are working on that regression problems or classification problems. We had an Excel file where we have X and then we have Y. Here we do not have such kind of thing. We have only the data folders. So in this data set folder, I have this all images. So whenever I talk about images, I am going to find out each and every image path. So I will use TQDM with TQDM. TQDM is going to create a progress bar. So TQDM is an iterator. Basically it will iterate as many times this for loop is getting iterated, and for every iteration of this for loop, P bar or the progress bar is getting updated by 1 unit. So the total of this progress bar, how many times it is going to execute, it is going to get executed the total number of image paths I have. So I am doing what, for each and every image I am trying to identify its label and store that label as well as the image array. Okay, so this progress bar will run n number of times. N basically represents the size of image, the number of images that I have. Then for IDX and image path, so when I am using enumerate, it will enumerate the images as well as path, which means 0 image, 1 image, 2 image. So it will store two things, it will give me two things, ID of the image and the path of the image. I am going to store image, I will read the image from the image path. So image paths is a list of all the images. If you talk about this image paths, it is a list of all the image paths, and I am reading one by one all the images from that image paths. I am reading all the images from that image path. So when I am using for loop, I will first read the first image path and I will store that image path as an image array. Then I will resize that image. I will reduce the size of the image by using cv2.resize. It will reduce the size to 28 by 28 that I am specifying here. You can use any choice of size. Once this resizing is done, which means the image can be anything of any size. Once the image getting imported, it will get resized automatically. First operation that I will do after reading that image is resizing that image of 22 and 28 by 28, so as to have uniformity of the images. Then we will convert that image to an array format. So image is resized and now the image is getting converted to array format and stored back to image. Now this image is nothing but an array of image, and in the empty list data I am adding that array. So in this empty list data I will add that array, and for the first image I have converted it to image. I have resized that image of 28 by 28 size. I have converted it to array and I have added it to data, and for that data I have to also generate a label. For that image I have to also generate a label and store inside the label labels column list. So for that I have to generate label. So to generate a label I will create image path dot split. So whatever is the image path, for example for a particular image, if I talk about say forest and this is the image, if we talk about this image, so forest the path of this image, I am taking this dummy path which is from localhost, but ideally the path of the image will look like this, and I want to, if I talk about the image path, the label of the image is present over here. This is the label of the image I want for that image. So this image, the label is this one. So what I will do is I will split this path into multiple items based on this separator, which is the OS path separator. Okay, so whatever is the OS, if you are using a Mac, it will be like this. If you are using something else, it will be backward slash. So I am separating the image with respect to the OS path. Now I separate it, and I want the second last element, this one. Okay, so if I separate it with respect to hyphen or forward slash, so this is the last element and this is the second last element. So I am using image path separator, and from that I am using the second last part. So os.path.sep will give me separator, so it can be forward slash or backward slash, okay, depending upon your OS. And image path.split, it will split that data or the image address, web address or the image address based on the image path. And -2 will give me the second last part of that image, which is the address, which is nothing but the label of that image. So label is going to be the second last part. So if the label is equal to buildings, I will put label value as 0. If the label is equal to forest, I will put label is equal to 1, and if the label is equal to C, I will put label is equal to 2. So as we know that in our case there are three types of folders. So if we talk about if we talk about our images, so the data set has CNN project, and if I go in the data set, I have three folders: forest, buildings and sea. So if it is forest and buildings and sea, I want to give it a proper label encoding. So I am doing label encoding itself here only, and I will add that label. So if it is say buildings, okay, the first image, if it is a building, automatically the label 0 will be getting added to the empty list labels. So labels is an empty list, on this I will be adding 0. If it is C, it will add 2 in the labels folder. So this way I am going to iterate over each and every images, and it will get stored inside the labels folder. Okay, labels list, and the progress bar is going to be updated at every. So this is the progress bar that I was talking about. So this is getting developed due to this TQDM library. If you don't want it, you can skip it, or if it is not working, also you can skip it. It is just to track the progress of my operation. Now if I talk about data 0, so you can see that this is the first image. So this first image, as you can see, it is an array, first, second and third. Okay, so maybe this is red, this is green and this is blue. This is the first image that we are talking about, and that's how, like, we have three red, green, blue channel. Okay, sorry, this one may be the red, then this one is green, there are multiple other things, and then blue. So basically you can see that 28 by 28 is the size of an array, and 3 are the channel. So if I talk about a single image, the image width and height is 28 by 28, and the channel, there are 3 channels of this image. So it is multidimensional image, multidimensional array. Now we will do what? We will reduce the images. So what are this number representing? These numbers are starting from 0 to 255 only. 0 being completely dark, or 255 being completely bright. Okay, so I want to scale this on a single scale, so I cannot use standard scaler or something like that, and I cannot do direct processing of that of these images. Okay, even though it is on a scale of 0 to 255, there are some values where I have 2 digit, and some places I have 3 digit number, somewhere I can have only 1 digit number, somewhere I will have 0. So the processing and computation becomes very difficult. So it is necessary to scale this data. That is why we are going to divide the each and every value by 255. We'll first convert it to NP array, and once we convert it to NP array, and we will divide it by 255. Now the data which was earlier a list is now a NP array, and then labels which was earlier a list, we will convert it to an NP array. Why we are using NP array? Because NP array, NumPy array, is faster compared to normal list. Now we are using labels. You can see it is an NumPy array of the categories, that particular images, whether it is building, forest and sea. We'll split the data. Now the data is nothing but our data, the NumPy array data and labels. We will split it into training and testing. We are putting a test size of 0.25 and training size of 0.75, and random state we are using 42 throughout, and we use train y. We have the train y and test y. Now when we are building a CNN model, we are using a complex architecture here. That's why it is necessary to convert the training, the Y data or the values into categorical format. So we are going to convert it into categorical format using two categorical. So we'll use two categorical over training Y as well as testing Y, and we have only three classes. So we are going to create as a categorical format with three classes. So if you see, we have three categories. So earlier it was 1 2 0 1 2. Okay, so this is 0, this is 1, and this is 2. So 2 basically represents C. So the first image in the training data is a C, and it is encoded, kind of encoded we have created. So we are using two categorical to encode the data. Why we are doing it? We have to map it with respect to our softmax function. That's why we need to do it. After that, we are using image data generator to augment the data. As I told you that image, a single image in a single proportionate cannot be used for further classification. So images needs to be oriented in different order. Okay, so while training an algorithm, it should not learn only if the data is in a certain angle. If I change the angle of the image, if I provide a new image in a different angle, it should be still be able to recognize what is that image. That is what the purpose of classification is. For that we will use image data generator. So we are using, it automatically generates newer array of images with respect to whatever specification you have given. So we are using rotation range 30, which means it will rotate 30° off and on, okay, on both the directions. So even if the image that we are providing is 30° tilted, it is fine, it will still recognize into correctly. Even if the image is shifted by range 0.1, which means, for example, the image is not the actual image and it is shifted, which means partially it is not visible. If the dog image, if I am talking about the forest image, if it is partially shifted to 0.1 unit, then also it is fine. We cannot have 0.2, 0.3. If we do it, so we will have more images generated and it will just increase the burden over our model. And that is why we will use 0.1. Right now I am using 0.1. If you have a model, if you have that computational problem, data computational efficiency, if you are using cloud or something, or you have a deployable application, you can increase this ranges and these angles as well. I am just doing it for the sake of demonstration, so that's why I am using very smaller numbers over here. Height shift, width shift is about shifting width, height shift is about vertical shifting, shear range is about 0.2. For example, complete image is not there, partially sheared image is there, so 0.2 degree shear is fine. Zoom 0.2 if the image is zoomed or a bigger image is there, still it will be able to. So I am using a zoom range of 0.2. Horizontal flip, if the image is completely horizontally flipped, still it should be able to recognize, the model should be able to learn from it. And fill mode is equal to nearest. Fill mode is equal to nearest is a method in OpenCV or image processing where if in case there are transitions happening in the data, so fill nearest method will use that nearest method of computational transformation of image. For example, say we have gradient, okay, we have sharp gradient between two images. So nearest method is the nearest interpolation method. We use Lagrange's nearest interpolation method to wherever there is a gradient or there is a sharp edge, and if the image is not, if we are not able to, or when we are capturing the image, something is missing while capturing that image, or something is not identifiable, it should use the nearest interpolation, which means if there is a white color next to this region, so if this particular part is not clearly visible, automatically it should take the white color because nearest region is white. So such kind of nearest Lagrange's interpolation method is used over it. So this is our augmentator. We have not yet augmented our images. So what we will do is we will call in we'll start with building the model and compiling it. So first thing that we are going to do here is we will call the model. So our model is LeanNet, okay, and we are going to build the model. We are providing width, height and depth of the model, and we are going to provide the classes. So there are three classes. We are using the optimizer Adam. We are calling it, we have already used or called the model. Then we are using compile. Compile will compile the model based on the loss, which is categorical cross entropy, and it will try to reduce the categorical cross entropy. And optimizer we are using Adam, and metrics we are using accuracy. We can use the model checkpoint for saving the optimal model, and we have compiled the model successfully. Now we are going to yeah, okay, yeah, we have compiled the model successfully. Now we will create a VGG model. So VGG model, here we are going to call the VGG16 model, build the VGG16 model. 28, 28, 3 is the dimension for the VGG16 model. Number of classes is 3. Here also we are using Adam optimizer and compile the VGG16 model. So for compiling loss we are using categorical cross entropy, and accuracy is the metrics which we want to govern. Okay. Now if we talk about the model summary, so first model is our LeNet model. So the model summary of LeNet model, we can see how many parameters. So initially the image comes and 1520 parameters of the weights we are going to develop, and slowly the weights are going to get developed more and more with respect to the activation function and the number of neurons that we are passing. And we are going to train how many weights? So we are going to train 6,03,673 weights total. These are all set of weights. In each layer we can see how many weights are generated. So wherever weights are getting generated, so convolutional 2D, there we need weights. Then convolutional 2D, second convolutional, where we need weights. Third convolutional we need weights. And here in the dense we are automatically generating more weights because we have specified 500 neurons. So based on the formation of these and these, we are getting this new weights. Okay, so if we try to multiply it, we can kind of get the weights over here, and that's how the weights are getting generated. 6 lakh in the LeNet model. And now we talk about VGG16 model. Here also similarly it starts. So this is how a LeNet model is constructed with 6 lakh parameters or weights. Now we talk about the VGG16 model. So in VGG16 as we discussed, it was supposed to have 16 convolutional neural network, but we have only 4 convolutional neural network. So it will develop the neurons or number of weights for this 4 convolutional neural network or convolution operation. And after that we have one dense and one dropout. You can see that earlier it was 256, 94, 208 kind of weights, and it is getting dropout, like we are using 50% dropout. So 1678, 1312 is the dropout, like half of it, like totally the weights are getting reduced. And finally I have only this 3 as our output in the dense layer. So here we can see in VGG model 42 lakh 74,790, okay, no, 4 crore 27 lakh 47,970. So here we are training more weights. VGG model, we are using more weights. So but obvious, VGG model is going to be very heavy compared to this LeNet model, and we have not even used 16 convolution operation here. We are just using simple convolution model. And now we will start with fitting the model. So when we fit this model, I have already run it, and we cannot spend more time on it. So I have already run it. So we just observe the output over here. So while fitting the model, so this is our model which we have created. So now we will fit the LeNet model over the training data. So here, if you remember, previously we have directly used x is equal to train and y is equal to test and something like that. But now here we will not directly pass in the input data. We will convert or augment it. We will do data augmentation while training the data. See, what is the best part of using this AUG? We are not saving anything in a physical memory. Okay, we are kind of using it on the go, and x is equal to AUG.flow we will use to create augmented version of images, and we will use train x and train y. By using train x and train y, it will create different versions of augmentation, like we have discussed earlier, shearing, width shift, and height shift, rotation, zoom, all this kind of different arrays will be created. And yeah, LeNet, here it is. So batch size is 32. I think we have discussed earlier, 32 batch size. Validation, we are using validation. So here we are using the original validation data, that is text X and Y. Okay, validation data as per the train test split. Steps per epoch, we are using the steps per epoch will be dependent on size of the training data divided by batch size. So whatever is the steps, how much steps we are going to implement, that we are going to use. Then epochs is equal to 50 we are using, and verbose equal to 1. So to start with, we can see that initially the validation accuracy is 0.653. It keeps on increasing, and to a point it increases 86, 87, 86. It keeps on increasing. Let's see if we are getting 90. So I am using very few epochs here, which is 50, and by 50 we are getting 8773 as the best so far. Maybe we have some best version above or below, but yeah, 8773 is the best. You can preserve the weights by using the checkpoint method that we have discussed in the previous classification method. If not, you can go ahead with whatever we have. Even this accuracy is best for the validation. So this is a validation accuracy. We are bothered about validation accuracy because validation data is a new data set on which the model will actually give some predictions. Okay, so if we are able to perform on the new data, which means that our model will perform on any kind of new images. So 87% accuracy is given by the LeanNet model. Then we will move forward with VGG16 model. In VGG16, we use the same approach. We create augmented by a type of images. Batch size we are specifying 32. Validation data, we are using the validation data in the train test split that we generated. Steps per epoch, similarly epochs is equal to 50, verbose equal to 1. Verbose is equal to 1 is just to present this information correctly. If you keep it 0, so possibly you will not see all the information clearly. So verbose equal to 0 is all about presenting this epoch by epoch information correctly. So you can see initially 40% accuracy, and slowly it is increasing. We are using 50 epochs. You can see accuracy is going below beyond 90 as well in some parts, like here at the end 90.61 is the accuracy. So it is much more reliable as we have higher accuracy compared to the LeanNet model. So it is giving good accuracy compared to LeanNet. So here if we talk about the LeanNet model, you can see if we compare the training and testing, so this code basically helps us to create a chart showing the accuracy of training data as well as the validation data. So accuracy of training data and validation data are kind of going in a similar order, higher in the upper range, and it is following the same trend actually. And same we will do it for loss, and the loss is also going down in the same order for LeanNet model. Similarly, if we do it for VGG16 CNN model, so it is also, so VGG16 is much more, you can see that it is overlapping, the validation accuracy and the training accuracy kind of overlapping over each other, and the loss also will get overlapped to some extent. It will not be, but yeah, it is comparatively better if you compare the loss of LeanNet with CNN VGG16 model. Okay, so after that we will create this TensorFlow.keras.preprocessing. Now we will use it over a new images. So for that, what we will do, say if I have certain images, I want to test if this images yeah. Now if I want to save these images wherever I have developed this processing, so we have successfully developed a CNN model and we have successfully trained it. We can now be utilizing it for further implementing over other images, testing other images, whether it is building forest or sea, so that we can easily do, we can use image to array. We are importing image to array. We are using load model to load the model if it is saved. NumPy we are using, image argparse, imutil, cv2, matplotlib we are using, and we are using image parse. So what we are going to do, first we are creating a function called as display image. This function is doing what? It will take an array and it will show that array as an image. Okay, so we are using figure is equal to plt.figure, using this plt.figure method from matplotlib, and axis is equal to figure.add subplots. We are using 111 subplot to show that image, and we are using ax.imshow. Imshow will convert that array into an image and show it as an image. Now here also let us just skip this part because we have already developed. Now we will talk about okay, just yeah. So we are talking about new set of images now. So there is a folder called as test examples. Okay, in my CNN project directory, if we talk about, there is a test example yeah, you can see test example. So here there are different images, and this is a mix. It is a combination of building, forest, sea. We don't know what it is. Okay, I will do what? I will call one by one all these images, and I will test using my model, and my model will recognize whether it is building or forest or sea, and it will label it on that particular image. So let us do it one by one. Let us call in these images. Let us call in these images and put a label on it. So first of all, we will use test image paths, and we will sort this data, which is first of all we will get the paths of all the images. The classes that we have is building, forest and sea. So 0 is building, 1 is forest and 2 is sea, and we are using TQDM. We are using the same for loop, and we are reading the images one by one from all the image paths that we have generated. So here we are using image paths over test image paths. One by one I will get one path at a time, read that path, and I will create an original copy of that path, and we will resize that image. Say this is why we are creating copy, because when I do pre-processing of the data now, so it will change the when I'm reading it, so it will change that particular image, maybe in black and white structure or something like that. So I don't want it to change the original image, and when I want to put a label, I don't want to change the label as well. So why we are doing it is, this is my original image and this is my image which I will be using for all the array operation and all. So I will first resize the image the way we are doing. We are converting it and dividing it by 255. We'll convert it to image to array. We are using expand dims to expand the dimension of the images, and we will use model.predict function. So predict function will predict what is there in that image. So I will pass this image array in this predict function. My predict function will learn what is there in this image path, and it will give me an array which is the probability of array like this. So I want, it is going to give me a nested array basically. Okay, nested list. I don't want nested list, I want the internal list, this one. So that is why we are using square bracket 0, and we will print the prediction of configuration, whatever is the prediction. Okay, once this is done, we are going to create a label. This label that we are going to create is nothing but np.argmax of predict configuration. So predict configuration is going to give me this list, and argmax will find out which part is maximum. Say this one is maximum, or this one maximum, or this one maximum. So it will give me the maximum value from this list. So from all classes, so all classes is what? This is my all classes, buildings, forest and sea, and below it say there are the probability values. So I will get the label corresponding to the highest probability value from all classes. So on all classes I will apply this np.argmax. np.argmax will tell me is this high, or this high. So say this is the highest, which is 0.8. So it will give me 0.8, the value corresponding to 0.8 in the all classes. So 0.8 is at second position. So what is at second position? Forest. So here forest will get stored. Predict conf will here we will get forest as stored, and we also want the probability. So if you want probability, so predict conf np.argmax predict conf. So it will tell me what is the probability of being that particular value. So it will give me the probability of that data as well. And what we are going to do, we are creating a label. It is a string value. This string value has label which is either building, forest or sea, and the probability of being a building, forest or sea. Okay, and then we are using output is equal to imutils and resize. It will resize the images, and it will IMUtils will resize the original image, and we will set the width is equal to 400, and we will put text on that image. So as I told you, when I use this image, so we are transforming this image continuously. So I cannot label this image now. If I want to put label on it, it will be difficult because it cannot be retransformed. So it is better to create a copy and put the label on that copy. So I have created this original image on which I will put label. Now what is that label? I am putting that label on the original image. So original image is stored as an output with which is resized and which is width is equal to 400, everything we have done. On that output is my original image. Now on that output original image I am putting a label which is our text format. We are specifying where to put this label and which kind of font we have to use. So CV2 has different fonts, so we have using font Hershey Simplex, a simple format we are using, and the position of the font and size and texture, everything we are specifying. This is the color, okay, this is the color of that font, this is the thickness or width, and this is like these are different attributes with respect to placing that text on that image, which means I have taken an image, I have tested that image, what kind of image it is, whether it is building forest and sea. I have stored that label into label. I have stored the probability. I have created a string label. On it, I have the label as well as the probability of that label. And then I am putting that label on the original image. So I have created two copies. So one copy will go for processing purpose in the machine learning or deep learning model, and the second will be used as a copy on which I will place the image label. So I will place the label on that copy, which is nothing but that same original image, and image will be used in the CV2.CV2 color in the original format. So earlier when we have taken the image, the image may not be in the color format when we are extracting the image. So we will convert it to BGR to RGB, which means we are converting the image when we are importing, it is always imported in BGR format, but what we want is it has to be in RGB format. So we will convert that image into RGB, which is the original image content, and then we will display image. We have already created this display image function over here. That function we will be using to show that image, and that's what is happening here. So when we run this, if you see, so yeah, so here when we run it, so we are taking one by one each and every images from test examples. So the first image, as you can see, it is actually a C, but it is trying to recognize it as building. So model is prone to make error. It is a linear model, so it will take it may take some error. This is also recognized as building and here it is recognizing C correctly, you can see. So it is able to recognize C correctly. This is C, this is also C, this is also C, this is buildings, which it is able to correctly not recognize with a very low percentage, 57. So maybe the model is confused. Here it is correctly recognizing, here it is correctly recognizing. Buildings it is wrongly recognizing. So it depends. So here it is correctly recognizing buildings. So it is possible. So the linear model, according to its understanding, it is recognizing whether it is building, forest and sea. Now the same kind of implementation is going to happen for VGG16. Only thing is the model is going to change. Earlier we have used model here. Here we will be using VGG model. Rest other everything will remain same, and here I have made a mistake. It should be VGG16 output images. Okay, so I have to store it in VGG16 output, and once this is done, you can see it is correctly recognizing this as C because it is a C. This is also a C, 47% confidence, 90% confidence it is saying C. This is also C, 100% C. So likewise it is correctly able to recognize C's and buildings. Sometimes it is making wrong predictions, like the earlier here it is correctly recognizing this as buildings. This is also a building, 98% confident, and VGG16 as said, it is giving a correct prediction compared to the any other model or compared to the LeNet model. Okay, because we are using a lesser number of neurons over there, So but obvious it is going to use less. So this is how you can implement a CNN model, take some images and classify it as any categories that you want, and this is the core foundation for any image processing library if you are working on any complex image architectures, image libraries. So we are using convolutional neural network as a backend in every image processing or classification exercise.